In this video, we're going to go over work and power. We will study the equations for both work and power, as well as little tips and tricks that you should keep in mind for your quizzes and tests. And in the rest of the video, we'll look over two practice problems that will demonstrate how these equations are applied when solving the problem. So you will learn a step-by-step instruction on how to approach any problem that has to do with work. Now, let's firstly start by examining these equations. So the equation for work is the following. It's force times displacement d times cosine of the angle between the force and the displacement. So for example, if we have a force that is being applied here, and let's say this object, right, is moving to the right, the force makes it move to the right. Work will be force times whatever displacement that this force is carrying it to, times the angle between, now if the displacement is in this direction, if the direction of motion is to the right, this angle theta over here will be over here between the force and distance, and the displacement, I apologize. Which, by the way, the error I just made speaking between distance and displacement brings me to the next topic, that this right here is not the distance, but it is the displacement. So remember that displacement is a vector, meaning that it can have a direction, right? Displacement is the final position minus initial position. So for example, if I, let's say, take an object and I move it all this way, let's say, and I come back to the same point, right? My final position, my initial position are the same. So for example, here, the displacement would be 0. So just like displacement, work therefore is a vector as well. So work can be positive or it can be negative. Work can have a direction as well. Great. Now that we have talked about, this is by the way what the second note says, that in the work calculation, it's displacement, right? Not the distance traveled. The second thing we should keep in mind is this equation for power. Power is simply a measure, right, of how long it took you to do a certain work. It's measured in the units of watts, and in order to calculate it, you just have to take your work and divide it by the time it took to complete that work. All right. Now let's take a look at some of the at basically the method, a step-by-step instruction for solving work-related problems. So essentially, first, our step will still remain the same as in the Newton's laws problems. We will sketch the free body diagram and figure out what forces are present and where are they directed. Some of them will be to the left, right, up, or down. And then I will also recommend put an arrow in the direction of motion, right? Because we need to know in which direction it's moving, and it will help us to figure out essentially what this angle theta is. The second thing will identify the angle between the displacement, so the direction of motion, and the force of interest, the force for which we're calculating the work, and essentially just plug it all into the equation, right? So a pretty straightforward method. Let's practice applying this method by looking at the following problem. Here we have a block of mass of 10 kilograms that is being moved across a horizontal surface for a distance of 25 meters. An external force of 100 newtons is applied at an angle of 45 degrees to the horizontal. The coefficient of friction between the block and the surface is 0.2. We need to calculate work done by each force. So this kind of comprehensive example will take us and introduce us to what could be the work done by each kind of force. So it's a really good example to introduce you to this concept. Then the second part, let's read later. Once we calculate the work, we'll calculate the power. So let's start by drawing, as always, our free body diagram. So we have our block, probably a favorite object in physics, and a force that is being applied at 45 degrees to the horizontal. Now, again, our direction of motion. So, well, before we even do direction of motion, what are other forces applied on this object? So I want you to think about this. So hopefully you said that there is gravity, right? Because there's always gravity pointed straight downwards. There's the normal force pointed upwards, the force from the surface. And there's also the friction force. If the object is moving to the right, because basically the force is pushing it to the right, the frictional force will be in the opposite direction, so to the left. Great. So now that we have calculated, let's find out the work done by each force. So let's start with work done by applied force. So our equation for work is force times distance times cosine of the angle between them, right? The displacement is to the right. So let me just maybe label even displacement, right? Over here. The displacement is to the right. So it's going to be, the angle is going to be 45 degrees. The force is 100. The distance is 25 times cosine of 45 degrees. And if we multiply all of that, you should get an answer of 1767.8 joules. If you plug that into your calculator and you got a different answer, just make sure that your calculator, go to mode and make sure your calculator is in degrees and not the radians. Okay, now let's calculate work done by friction. Work done by friction. So friction is, first of all, again, let's start with our generic formula, force times distance times cosine of the angle between them. So force is the force of friction. Therefore, the formula for the force of friction is mu times n. As we see here, the normal force, right, is equal to mg. So it's going to be mu times mg. Great. We do know m, we do know mu, the coefficient of friction. So therefore, we can plug this in here, right? And we know the distance or the displacement essentially. Now let's talk about the angle, right? So the friction is to the left, but the object is moving to the right. So the displacement is to the right, but the friction is to the left. So the angle between these two is 180 degrees. So cosine is 180 degrees. If you think about this for a second, it makes sense, right? The friction does negative work on the object. It takes away energy, in other words. And if we develop this idea a little bit further, friction will always be pointed opposite to the motion, so opposite to the displacement. So essentially, friction will always be cosine of 180, right? And cosine of 180, if you remember your unit circle, is just -1. So friction will always be negative, right? Once you kind of see it once, it'll be easier to figure out work done by friction in the future. It'll simply be negative force times distance, right? Because it's always going to be 180 degrees. Okay, now that we have all of this, so it's -1 times mu is 0.2, right? Mass is 10, g is 9.8, and the displacement is 25 meters. So if we plug all of that in, we should get an answer of -490 joules. Oh, by the way, the units of work are joules. Okay, what about work done by normal force? By normal force and mg. So let's take a look at this. Work done by normal force. So force times distance times cosine of the angle, right? N times distance. But what is the angle? So the normal force is pointed upwards, but the displacement is to the right, as it has been before. So the distance between these two is 90 degrees. And cosine of 90 degrees is 0. So work done by normal force is 0, and work done by the gravitational force will also be 0, because the angle between the gravitational force mg and this displacement is 0 as well. Conceptually, you can understand it in the following way. Normal force and mg do not contribute to moving this block to the right. Therefore, they're not doing any kind of work on this object. The only forces that are doing the work, right, are this applied force F and the friction force right here. So to find the total work then, we can just sum work done by the applied force, 1767.8 minus 490, work done by the friction. And the final answer is going to be 1277.8 joules. All right. Now we can just quickly finish this example by talking about power, right? So power is simply going to be work over time. So if we want to calculate the power done by the applied force, we can just take the work that was done by the applied force, 1767.8, and divide it by time, which is 10 seconds. So moving one decimal place here, we get power of this, and power has units of watts. So here's our final answer. Great. All right, so let's take a look at the next example. And here, this problem is going to be really, really quick. In this problem, a hiker carrying a backpack with a mass of 20 kilograms plans to climb a hill that is 500 meters high. The path to the top makes an angle of 30 degrees with the horizontal. The hiker moves at a constant speed, so no acceleration, implying, right, that's what it says. Calculate the work done by the hiker against gravity. So basically calculate the work done by the gravitational force. Well, let's take a look. As always, I will start by drawing a picture, right? So here's our hiker. Now, we're really only concerned here with mg. So therefore, that's the only force I'm going to label here because I only need to find the work done by mg. So mg is pointed downwards, but the height, right, or the displacement, so he starts here and ends here. So the displacement is in the upward direction, right? The displacement here is equal to 500 meters. And the force is equal to mg, or 20 times 9.8. Now, what about the angle between those two forces? So if the mg is down and the displacement is up, the angle between these two is going to be 180. In other words, right, when you're climbing the hill, you have to overcome gravity. So gravity does negative work. It doesn't help you to move up the hill, right? It actually hinders you moving up the hill. So work will be equal to force times distance times cosine of 180. Once again, cosine of 180 will be -1. So again, mg does negative work here. So negative times f, right, is mg. So minus 20 times 9.8 times the distance. We get a final answer for work as 9,800 joules. Now, why did I include this problem? What does this problem demonstrate? What it demonstrates is that what matters, right, when we're talking about the work is the displacement. It doesn't matter what path the hiker took, or that the path was 30 degrees, right? The only thing that actually matters is how much, what was his final displacement. So his initial height and final height, where he ended up, right? That he ended up 500 meters away from his initial point, in other words, right? He could have taken any path, right? Work does not depend on the path that is taken. It only depends on the displacement. And you could be tested on this principle either through a problem like this one or maybe on a multiple choice question. So I wanted to make sure that you understand this. In the next video, we're going to go over plots that have to do with work. Another very important concept that is going to be, I think, pretty quick and pretty simple, but is going to demonstrate another important subtype of work problems. Guys, keep practicing and you can conquer physics, and keep working through these examples and watching these videos on your way to an A. Thank you.